One moment. Okay, everyone can hear me and see my slides? Very good. One second, I have to move one other thing out of the way here. Okay, well, thank you to the organizers for the invitation to talk. Hello, everyone. And so I guess we'll continue the discussion of quantum black holes. I've long believed, and I think others probably do to varying degrees, that the problem of black hole information is really a key problem for quantum gravity, much as understanding the atom was a key problem in the development of quantum mechanics. And so if that's true, we should be able to use it as a guide to the new principles of quantum gravity, whatever they are. And even more interestingly, we may learn from this that there are observational signatures of quantum gravity. That is something worth seriously considering. So the talk today will update some perspectives on this whole story. And there are a number of perspectives, as I think we've been hearing, on the problem, and a number of proposed resolutions, some of which have been represented at this conference. For example, there's been a lot of recent focus on entropy calculations, as we've just heard from Tom's very nice talk. I just want to remind people, though, that entropies are just one diagnostic of what's going on. And I'm going to take a slightly different tack and suggest a way of organizing our understanding of the problem, which connects to an information theoretic perspective, but looks at maybe at some of the more basic issues and certain questions that could be important. And I'll organize things by stating what I'm going to call a black hole theorem. And I'm putting that in quotes for various reasons. One reason is I view this as a theorem to be taken in the spirit of the Coleman-Mandula theorem. And of course, the important thing about the Coleman-Mandula theorem was the loophole in the theorem, and that was where supersymmetry came in. So here too, as I'll say more, the important thing is probably, how do we get out of the theorem? What's the loophole? So a first statement, version 1 of what I'm calling the black hole theorem, again in quotes. If a black hole is a subsystem, if distinct black hole states have identical exterior evolution, and if the black hole subsystem disappears at the end of evolution, then this violates quantum mechanics, specifically unitary evolution. Now that's a set of statements you could make for other systems with subsystems, but here we're going to focus on the black hole context. And it's important to clarify what we mean exactly by these assumptions or statements. So I'll at least describe a little bit more in detail what those involve. So first, a black hole is a subsystem. Well, in a lot of the literature in recent years, colloquially, a subsystem has been described by just saying that the Hilbert space factorizes into a product of the black hole part of the Hilbert space and the environment, the rest of the universe. However, in local quantum field theory, that kind of factorization can be rather problematic. One way of saying it is due to the type 3 property. So let's be a little bit more careful. And so here I've drawn the classical space-time of a black hole, either a Penrose diagram or an Eddington-Finkelstein diagram. I'll use Eddington-Finkelstein diagrams more typically in this talk. And I've shown a slice through that geometry in the two pictures. And the idea is that we can write the state on the quantum state on the slice in terms of a part that corresponds to, so to speak, the excitations inside the black hole, and a part that corresponds to the excitations in the environment, in the complement. So the idea of, well, one way of representing what we mean by subsystems is that you can write the state in that fashion. At a more formal level, one often speaks of there being operator subalgebras. And again, this is at the level of local quantum field theory. operator subalgebras that commute that correspond to things that create or measure excitations either in the black hole or in the environment. There's also a way of doing something like a factorization involving the split vacuum. I won't talk about that. That requires some modification of the state, but at least that gets us back towards this more familiar to some story. But that's what I mean by a black hole being a subsystem. I'm just describing it in the local quantum field theory approximation right now. And I think this is likely an important point. Local quantum field theory and other quantum systems have the structure of subsystems hardwired at the beginning. That's part of the underlying structure of the theory. And a big question in my mind is, what's the analogous structure in the context of quantum gravity? We'll talk more about that. Okay, next, distinct black hole states have identical exterior evolution. Well, again, we can illustrate that in this kind of picture. We have an initial slice like I described, and evolution to a later slice. And if you consider the evolution of local quantum fields on a background, you know, for example, if you have an excitation here, then that stays within the light cone, and the light rays outward and inward going are shown by the blue lines. And so that excitation, whether it's in one configuration or another, doesn't affect the external evolution of the state. Okay, so the state evolves such that this exterior part, or the environment part, is independent of what that excitation was. And so a very concrete realization of that story, you know, you could state that more generally. A concrete realization is this local quantum field theory evolution on a background, where we can write down the evolution operator. And, you know, making that very concrete has been one of the goals of some recent work that I've been doing, just to spell out more the details of the evolving quantum state, both in lower dimensions and in you know, full 4-dimensional or higher story with a student at Santa Barbara. Now, one way of characterizing this statement that the exterior evolution is independent of the interior state is to write down something like a density matrix, where we trace over the internal degrees of freedom. And we would say that that density matrix is independent of what you started out with for the internal part of the state. There is a bit of a challenge here, because writing down a density matrix like this by tracing is sort of a cutoff dependent prescription. There's a whole question of how to properly do all of that. Another way that avoids some of that story is to just think about operators that correspond to observables in the environment and look at their expectation values in the evolving quantum state. And then the statement is that those expectation values are independent of whatever you started out with the internal part of the quantum state, for all such observables in the algebra of the environment, so to speak. Okay, so this, again, set of statements can be made more generally, but in local quantum field theory, this exterior evolution being identical is guaranteed by the property of locality. That's what's telling you that these excitations don't get outside the light cones. Of course, the story I've given here in illustrating the basic statements ignores gravitational back reaction, shrinkage of the black hole, but you can even correct for that at leading order. The leading semi-classical corrections can be studied by taking into account the back reaction of the Hawking radiation, like we did in the 2-dimensional CGHS models. So you can take this one step further. Okay, finally, the third assumption, that the black hole disappears at the end of evolution. So we've described the structure of the state, and then what we mean by it disappearing at the end of evolution is that whatever the evolution operator it is, it takes it to a state of the environment with no more black hole, and that state is independent of the internal states of the black hole. And once we've stated what this means, then the theorem is really follows trivially, because this represents many to one evolution. And so if we have an evolution operator that does this, it must be non-unitary, and therefore we violate quantum mechanics. course, one diagnostic of all of that is to look at, say, entanglement entropies. We could take the internal states of the black hole and entangle them with some auxiliary system. This happens naturally with the early Hawking radiation. And we could represent this situation by saying, before it disappears, we have non-zero entanglement entropy, but if it disappears, the entanglement entropy goes to zero. And so that represents the conflict with quantum mechanics. There are various ways of saying it, but this is essentially what's going on. Okay, so to save quantum mechanics and evade this theorem, we need to violate clearly one or more assumptions. So again, like with Coleman-Mandula, the key point may be finding the loophole, which could be guiding new principles of quantum gravity. There are various proposed outs. We've heard about some of them, but a good test question is to bring it back to how your proposal, whatever your favorite proposal is, how precisely it differs from the local quantum field theory evolution, which gives you the Hawking picture. And we have an increasingly detailed story regarding how that works, and for example, in real-time evolution. And part of that question is, how does your picture alter these assumptions, your favorite picture, and what other assumptions are required? And there are a number required. So let me just go through some scenarios that have been considered over time. One is microscopic remnants. And if you have a microscopic remnant left at the end, that violates assumption 3, disappearance. But of course, it introduces other problems, for example, infinite production of those remnants. And there's some discussion of that, for example, in these references. Another picture that's been considered for a long time is that a black hole at some point in its evolution transitions to something else, which we'll just call a massive remnant, which is different from a black hole. This happens while the black hole is at a size that's very large as compared to the Planck mass. And there are various realizations of this basic picture. The fuzzballs, firewalls, gravistars, Planck stars, the list goes on. Others, I think, maybe have been touched on in this meeting. If this is the picture, then we're modifying the statement that black holes are subsystems. You have a different kind of subsystem structure. And of course, you're modifying the form of the evolution. Another popular story has been ER equals EPR, which suggests a different subsystem identification, but there's a question in my mind of how that really systematically works. Then there are other scenarios, some advocated by a Tuft, various others, again, some mentioned at this meeting. Those are left as an exercise for the listener. But of course, one very popular and interesting scenario is that of replica wormholes, which we've just heard about. And I want to say a few more words about that. So I've given an incomplete list of references. Tom was more complete, but of course the list is much longer. The basic idea here, as Tom nicely reviewed, is that we have two curves we have known for a long time. One is the rising curve of the entanglement entropy of the Hawking radiation with the states of the black hole. And the other is the falling curve of the Bekenstein-Hawking entropy, which we think might represent the number of possible states of the black hole. And of course, Don, I think, was the first one to argue clearly in print that if we have a unitary story, then we should follow a curve that's the lower of the two. And the replica wormhole story basically gives us a sort of prescription for choosing the lower of the two curves, which Tom has motivated from formal arguments based on the Euclidean path integral. But there is a question of how we relate this whole story to the standard quantum language of states and amplitudes, or does it represent some generalization or modification of quantum mechanical rules at a more basic level? And there's some brief discussion of that question in this paper with Turiachi. If we do want to relate to states, amplitudes, etc., the best bet seems to be the possible connection with baby universe emission, which has been explored by Meroff and Maxfield and various others. And a picture might be something like this, that we have a black hole and a piece of its interior branches off into a separate baby universe. Something like that could happen as part of the explanation here. That seems like that would be a modification of the subsystem structure. You have information going off into the baby universe state. But let's think about how to describe that. And in fact, this kind of process was studied in a fairly general way in an approximation, which could be important in this work long ago of Pullman and myself and Strominger, baby universe emission. And essentially, you can summarize the effects of these baby universe emissions in terms of a term, say in the Hamiltonian, that corresponds to annihilation or creation of the baby universe. So it acts on the baby universe part of a new Hilbert space of baby universes. And then times an operator that summarizes the effect on our state in our universe. This isn't an approximation where the baby universes don't interact. You have just a term of this kind. And then the observation was that you can always diagonalize this operator A plus A dagger in what's called an alpha vacuum. And then once you've done that, that you have a situation where you have a Hamiltonian, if you're in a definite alpha vacuum, a Hamiltonian with a correction that just involves the operator acting on our state times something that plays the role of a coupling constant. So if these operators are localized inside the black hole, it's hard to see how that helps avoid the conclusions of the black hole theorem. The couplings are changed, you have some new operators, but that's it. The one possible out is if the operators are non-local on scales of order of the black hole size, corresponding to, say, big baby universes, then you might violate assumption 2 and have outside evolution depending on the black hole state because those operators reach out beyond the horizon. So that would represent some kind of new non-local interactions being introduced. I'll return to that question later, but that's at least one attempt to try to interpret what's going on. Maybe there's some other interpretation, but what is it? We really need a clear explanation, I believe. But I'd like to return to a more general discussion and go back to our assumptions and ask how much new structure really needs to be introduced, and are there less drastic modifications to the story that achieve the rescue of quantum mechanics? So first, let's talk about this assumption that a black hole is a subsystem. What is a subsystem in gravity is an important question. In general, answering that question is an important basic concept in studying any quantum system. So again, for finite or locally finite systems, like on the lattice, we represent subsystems by saying that the Hilbert space factorizes. And one reason for that is you want the structure where, say, a measurement in one subsystem is independent of the state in the other subsystem, the complementary subsystem. So that's the basic structure. As I've said, in local quantum field theory, that's not quite how we usually do things. Instead, we think of the algebra of observables as being composed of putting together algebras corresponding to, say, different regions. That's described nicely in the book by Hogg and other references. But let me give you a simple example. So if we think about, say, a scalar field, and we have a neighborhood here, then we can take the vacuum and act on it by an operator that looks like this, where J is a source of compact support. And if we're in this new state and we go outside the neighborhood and measure, say, the expectation value of the field, well, that expectation value doesn't depend on the fact that we've created these excitations in this neighborhood, okay? So that's how we're encoding the subsystem structure. We have excitations in here and measurements out here that are independent of those. And so that's local quantum field theory, and Hawking evolution respects that description of subsystems, and that's what constrains the escape of information and gets us into the trouble we have. There's a question of how to think about subsystems in gravity. First of all, if you have a scalar field, say, or any other local quantum field, the field is not gauge invariant. It doesn't commute with the constraints. And likewise, the state I've described is not a gauge invariant state. It's not annihilated by the constraints. And so here the constraints I'll call C mu of x. And at least in the effective description where we're basically thinking of quantizing GR, those constraints are gotten by writing down the 0 mu component of what would be the right-hand side of Einstein's equations if we put it all on the right-hand side, so to speak. And so this statement that you're not gauge invariant, these are not gauge invariant, physically corresponds to the fact that a particle is inseparable from its gravitational field. You have to include its gravitational field in its description. So how do we do that? Well, we can solve the constraints by constructing what's known as the gravitational dressing. We can do this perturbatively. And so let's think about, say, working about some background metric and perturbatively quantizing using a metric fluctuation. Here, kappa is basically the square root of Newton's constant. And at least to leading order, we can understand how to solve the constraints by constructing an operator that involves this metric perturbation. So we take, for example, this state where we've created an excitation in a neighborhood, and we can promote it to a dressed state, which involves both the original, say, scalar field and the metric perturbation. So an operator that involves those acting on the vacuum. In the form of this state or of that operator can be written as the original, say, state times the exponential of the integral of a certain functional of the metric perturbation times the 0 mu component of the stress tensor. And likewise, the dressed operator is gotten by conjugating the original operator by a similar expression. So that's been worked out in detail in these references, both in flat space and ADS. And in fact, these functionals, the dressings, are not unique. There are many possible choices corresponding to different gravitational fields we could put around a given, say, excitation. In pictures, and finally, more recently, a similar story, or the same story has been studied in some other work here. So the picture is that here we have our state with some excitation in a neighborhood, but you have to include the gravitational field of this gravitational dressing going out to infinity. And that gets in the way of the usual definition of subsystems. Now, for example, these dressed operators won't commute because the gravitational dressings run into one another, so to speak. And that's explicitly been shown and studied in these papers. And for example, if you take an operator that creates an excitation plus its dressing, and then you go outside, so you have this, you create this state, which I call J hat, and then you go outside and say, look at the expectation value of the, say, metric perturbation. You get a non-zero answer that depends on the fact that you've created this excitation, because you can effectively measure its gravitational field. So the structure is different. So there's a question of, in what sense does information truly localize in quantum gravity? What is a subsystem in the context of quantum gravity? And again, I want to stress, it looks to me like this is a key underlying structural question in quantum gravity that we need to better understand. We have understood some aspects of it, and here are some results. First of all, I said there were choices of this dressing, and in fact, the perturbative dressing can be chosen so that, say, in one of these states, if you look at endpoint functions of the metric perturbation, those only depend on the total Poincare charges of the state you created inside the neighborhood. And so you don't have, from this perturbative, or from these perturbative endpoint functions, you aren't sensitive to all the details of that state, just the total Poincare charges. That, by the way, suggests a limited role for this whole soft hair story, which has been rather popular, because these are the things that are basically measuring the soft hair. And we're saying, those really only have to be correlated with the Poincare charges of the matter you have in a given region. On the other hand, there are observables that can see the stress state from afar. And that comes from, well, you can understand that by looking at the translation generators. The translation generators in gravity can be written as surface terms, the ADM surface terms, plus an integral of the constraints. And so the statement is that if we've solved the constraints, set the constraints to 0, then the translation generators are operators that purely live at infinity. And so Merrill proposed an explanation for holography in ADS based on this. The picture of how you relate bulk and boundary operators is you can relate, say, a bulk excitation or operator here to a boundary operator by following the evolution forward. But then once you've represented that as something on the boundary, you can effectively translate it back using this boundary operator, the Hamiltonian time translation, to translate it back to an operator, say, at equal times. And that is an operator that is capable of, say, observing this state. In fact, there's a simpler version of that argument, never mind propagation and translating back. You can just take the operator here, or the state here, and translate it out to the boundary using a spatial translation by the same kind of construction where, well, you effectively have the spatial translation generator being an operator that lives at the boundary. So concretely, if we have address state, then there are operators that live at the boundary which are sensitive to the fact that in fact, potentially the details of that state that you get by, say, operating on the state with a translation operator, which brings it out to the boundary, and measuring the state with some other operator. So that looks like it's sensitive to the details of whatever state you have in this neighborhood. So that's suggesting that information is, in a sense, delocalized in the context of gravity. Some notes, though. First, you have to solve the constraints for this to work. You have to have a solution to begin with. Secondly, in general, we need a non-perturbative solution, and there are a couple of ways of illustrating that. For example, if you think about, say, two states, different states inside a black hole, say corresponding to exciting two different scalar fields with the same source, if you want to tell the difference between those, then clearly you need this construction to work at the full non-perturbative level to be able to sort of pull the excitations out and measure them at infinity. And also, in order for this to work, say in ADS or in flat space, if you're working off at infinity, you need a large translation. And that also involves the non-perturbative structure of the constraints. There has been some argument that this whole story extends to perturbative availability of information, but the relevant terms that they talk about are exponentially small, and things like, the displacement you need times the say mass of the typical excitation of, say, your scalar field. So that's an important question. So in particular, taking into account the various limitations that come from these statements, there is a question of what sense is information effectively delocalized, which we have not completely answered. But in short, it looks like, well, or let me put it this way. In short, there's a real question of whether these kinds of effects are sufficient to communicate information outside a black hole and resolve the problem, or is new non-perturbative structure needed? And in fact, the statement that we need to solve the constraints to be able to use this kind of construction tells us, and we need to non-perturbatively solve the constraints, tells us, in a sense, we have to solve the problem of black hole evolution and information in order to solve the problem. So it's not clear it really helps us, at least at this stage. But let's go back to our assumptions. And here I've added quantum mechanics as the first assumption. So these are the four assumptions that are in conflict, and let's look at different ways of reading that conflict. So if we assume that quantum mechanical evolution holds and black holes disappear, that tells us that one or two or both fail. You can think of that as a sort of non-locality theorem. This is version 2 of this theorem. And so that's telling us there has to be some important departure from the local quantum field theory paradigm. But I think it's quite plausible that there is an effective description of subsystems that's true to a good enough approximation in this story. And I'd like to consider for the last part of the talk that possibility that we can think of at least an approximate decomposition into subsystems for purposes of studying black holes, and follow the logic of what we learn if we take that to be true, if we find that to be true. So if that's true, then quantum mechanics plus subsystems plus disappearance tells us that distinct black hole states do not have identical exterior evolution. So that's version 3 of the theorem. And in other words, we must have new black hole state dependent interactions. There must be interactions that effectively transfer information from the internal state of the black hole to outgoing excitations. And so that's a story I've studied in a series of papers, some of which are listed here. Now, such black hole state dependent interactions violate semi-classical locality. Of course, that's with respect to the classical geometry, which we know is not the full story. But what I've proposed to do is explore those in a principled parameterization of ignorance, and a brief overview is, say, in this reference here. So we write the state in the way we've been writing it, the internal part and the state of the environment. And local quantum field theory evolution gets us into trouble, but we need a correction to that, which we're going to parameterize. And that correction, delta H, needs to, like I said, transfer information from the internal state of the black hole to the state of the environment. And the simplest possible form of an interaction that can do that is something that's just bilinear, an operator that acts on the black hole part of the Hilbert space. I'll just write down all possible such operators, times an operator that acts on the environment. And we might have a sum of terms like that. Now, if the environment of the black hole is to a good approximation described by local quantum field theory, we can think of building these these environment operators from local quantum field theory operators. That's a good description. What else can we say about the structure of these interactions? Well, first, we expect that they act on a scale of order the event horizon size. And here we could also make contact with that wormhole discussion that we had earlier. That's the natural scale. These operators have to at least bring information outside the horizon, but there's no reason for them to be fine-tuned, so they only imprint information, say, a Planck length outside the horizon. The natural scale is imprinting information on a region of size of order the horizon size outside the horizon. And that avoids unnatural things like firewalls. And one way of motivating that is really I think if you consider it carefully, there are good arguments that that's where the black hole radiation is produced, not at a Planck length from the horizon, but in this quantum atmosphere region that has a size of order the event horizon size surrounding the event horizon. Another point is that it's a reasonable hypothesis that these couplings are universal to all different kinds of matter and fields. That both preserves a large part of the very pretty story of black hole thermodynamics, and addresses certain Gedanken experiments involving what's called black hole mining, and also reflects the general universality of gravity that we find in nature. So we can satisfy those conditions by rewriting these operators as just couplings to the stress tensor with what are effectively form factors. And these form factors have support on scales of order the event horizon size. Then we can take this expression and we can reorganize it by combining the operators acting on the black hole part of the state and these form factors. We can reorganize it as something that looks like what is effectively a metric perturbation times the stress tensor. But this is a black hole state-dependent metric perturbation. So that is, with these assumptions, the form of the interactions. The next question is, what other constraints should these obey? And there's one other very important constraint, that these interactions need to transfer information or entanglement at a certain rate to undo the damage done by Hawking radiation. Namely, they need to transfer entanglement at a rate of 1 qubit per light crossing time in order of magnitude. And there are two ways of achieving that. One is if in the typical black hole state, these metric perturbations are of order 1, clearly that's sufficient. If you have an effective metric perturbation that's varying on scales of order R with the magnitude of order 1, then that can transfer enough information to the quantum state. That's what I'll call a strong or coherent scenario. And so such order 1 metric perturbations, effective metric perturbations, would of course potentially be very important, because that could distort, say, the images seen by Event Horizon Telescope in a time-dependent fashion. And that's something we've looked at some. I looked at with Demetrius Saltis, for example. And really just based on the images we have now from the Event Horizon Telescope, one is really, if you're careful about it, putting bounds on this kind of scenario. But there's a question of what size of these couplings or effective metric perturbations is truly necessary to transfer this amount of information. And here this touches on a general question, which is the question of information transport rates between subsystems for given couplings between the subsystems. There's a conjecture that we've made about those rates with certain assumptions, but a simple way of explaining an estimate of the rate is that basically if you have two subsystems with a coupling, you can think of the information transfer rate as closely tied to the rate at which one subsystem decays by creating an excitation in the other. And that's that kind of rate you can calculate by Fermi's golden rule. You have that rate is 2 pi times the density of final states times the matrix element of the perturbation in the Hamiltonian squared. The density of final states, since the final states include the black hole states, can be exponentially large. And that means that these matrix elements of the perturbations actually can be exponentially small and still achieve the needed rate, which is 1 per light crossing time. And so in that scenario, it's easy to see that likewise, you will have a typical expectation value of the metric perturbation, which is also exponentially small. In that scenario, it looks like one can also achieve the required information transfer, but with metric perturbations, which are effectively much smaller. So I'll call that the weak or incoherent scenario. It's going to be harder to see these, obviously, by Event Horizon Telescope observations, but there's a similar argument of if you consider scattering of a gravitational wave off of a black hole in the presence of such interactions, and look at the amplitude for scattering induced by these interactions. And you can also get order 1 corrections by the same kind of argument about the parametric dependence. Basically, you can get order 1 corrections for wavelengths of order the event horizon size. And so that means that you can modify the gravitational wave scattering, the absorption and reflection is modified by these corrections. And of course, important components of the LIGO-Virgo signal involve wavelengths of order the event horizon size. So that offers a possible way of going at observational signatures there, and that's something that we're looking into. So I think I'm out of time. Just to summarize, I've listed this set of assumptions that are in conflict. Quantum mechanics, the black hole is a subsystem, distinct black hole states have identical exterior evolution, and black holes disappear at the end of evolution. It's helpful to understand how a given scenario evades this. And the question is, can we do so with minimal new assumptions and without dramatic new structure? This general question of subsystems and gravity is a very important one. It seems like a basic structural question in quantum gravity. We have some results, but also some remaining puzzles. And then finally, one way of organizing this theorem is to state that if quantum mechanics holds, if there are subsystems and if black holes disappear, then there must be new interactions which are non-local with respect to the semi-classical description, which we can make a principled parameterization of, and which lead to possible observational consequences. So I'll stop there and take questions. As the last speaker, let me just say thanks to the organizers for putting together this stimulating conference.
Okay. Well, thank you very much, Steve. And so are there questions?
Yeah, actually, I have a question. Can you go?
Go ahead.
Yeah. So, yeah, I really enjoyed the talk. Thank you. So my question is, so the space-time for an evaporating black hole in GR, even Schwarzschild, is not globally hyperbolic. So, which means that, I mean, you may see, if I see your list of assumptions, so there is, for instance, so I can agree with 1, 2, 3, but if I restrict my attention to only the maximal equation development, then your pure state does not need to evolve into a pure state in quantum mechanics because you have a Cauchy horizon, right?
Because of what?
A Cauchy horizon. So there is some portion of space-time which is in the causal future of the singularity, and you cannot evolve it. So even if even if the evolution operator is unitary, you cannot evolve a pure state into a pure state because you have to evolve through the singularity, right?
Well, yeah, so there's the question of what to do with the singularity. Now, of course, I've motivated these assumptions by referring to the classical picture. That's what I did earlier in the talk. But now let's just take away these assumptions as basic assumptions, not tying them to a space-time picture. And I think they stand on their own. There's this notion of you have black holes being subsystems of a bigger system, distinct black hole states having identical exterior evolution. And finally, we explore the possibility that the black hole disappears at the end of evolution. So the black hole subsystem is no longer there. And that's associated with what you just said, but let's just say we try to parameterize that happening, okay? And if that happens, we have non-unitary evolution.
Yes, no, I completely agree, but also in, so the portion of the space-time which is in the causal future of the singularity, because at the end of the evaporation, you have a naked singularity, right? Because
well, that's the question. That's very much the question is in the true quantum theory of gravity, what is the outcome of that? And there are various arguments that the outcome must be that the thing disappears, because the alternative is if it doesn't disappear, then you're left with, say, something like a remnant, okay?
Yeah, no, sure, so, but what I mean is 2 would not be valid because whatever happens due to quantum gravity will modify what is, at least in its causal future, right? So,
there's a general story there too that you might say, well, the question is when is 2 violated?
Yeah,
that's really the question, the important question. And if 2 is violated while the black hole is still big, then I've been parameterizing a way that could happen. It goes outside apparently of local quantum field theory. If 2 is violated only once the black hole reaches the Planck size or something like that, where the calculations of semi-classical gravity break down, then there are general arguments that you must have a long-lived remnant because it takes a long time based on constraints of energy conservation outside for the information to get out. So you must have a long-lived remnant, and then that lands you in this whole set of problems with remnants, even if it's long-lived but eventually decays. Mm-hmm. So that scenario is commonly believed to be ruled out, basically because of all these problems with remnants with unbounded numbers of internal states.
Okay. Thanks.
Sure.
Okay, are there any other questions for Steve? Okay, let's see. I say in this, I'm sorry we're running late because of my unpreparedness. I forgot that I didn't have everything set up in my office and I had to come to